So let's talk now about the chemical reactivity of alkenes. So we know that alkenes are unsaturated hydrocarbons and they have double bond. The double bond here is the functional group in the alkenes, and because of the presence of the double bonds, alkenes are much more reactive than their alkane counterparts. So alkenes are electron rich because of the double bond, and this is why they are more reactive and they can have a variety of reactions. The most characteristic reaction of alkenes is the addition to the double bond. So the first type of reaction, which is addition to double bond, is the catalytic hydrogenation. And hydrogenation here means addition of hydrogen. So the hydrogen will be added to the two carbons in the double that have the double bond. So we will end up with a saturated hydrocarbon. So when you add hydrogen to the double bond, you will end up with a saturated hydrocarbon. So you will end up with an alkane. This reaction is called catalytic because it needs a catalyst. This reaction doesn't proceed without a catalyst. So an alkene with hydrogen will not react without the presence of the catalyst. So alkene and hydrogen alone without a catalyst, there will be no reaction. So we need a catalyst here for the reaction to proceed. The importance of the catalyst is to reduce the activation, lower the activation energy for the reaction. So when you add a catalyst, then much lower activation energy is needed for the reaction to take place, so the reaction can easily take place to give you the product. If you have no catalyst, then the reaction will need very high activation energy and it will not take place. The second type of addition to double bond of reaction for addition of double bond to addition to double bond of alkenes is the electrophilic addition. So electrophilic addition, let's first talk about what is an electrophile. What does it mean, electrophilic addition? Electrophile from the word means that it's something electron lover, because phile means lover and electro here means electron. So it's a group or it's an atom that is deficient in electrons and it loves electrons. So it wants to it will be attacked by electrons, or it will react with electrons or add itself to electrons. So these electrophiles are Lewis acids, and they act as electron pair acceptor in a reaction based on the alkene acting as electron pair donor. So the alkene itself, because it has a double bond, the pi bond here, or the electrons in the pi bond, are easily breakable, so they act as electron pair donor. And then we have an electrophile, which is electron deficient, so it will act as electron pair acceptor. So now the double bond here is electron rich, and then we have some sort of polar reagent. Polar reagent means that there is a bond here and two groups or two atoms where there is a partial positive charge on one and a partial negative charge on the other. And this sign here means partial positive and partial negative. It's not completely positive and completely negative. And what do we mean by the word partial? It means that the bond here still exists. Okay, so the bond between A and B still exists. It's not broken, but the electrons have more tendency towards towards B than A. This is why the B has a partial negative charge and A has a partial positive charge. So the A here is because it has a partial positive charge, it's electron deficient. So it will act as an electrophile. So let's see an example to understand more how does this reaction proceed. An example of that is the hydrohalogenation of to a double bond of alkene. So hydrogenation of alkenes means addition of hydrogen with X HX. So and X here is a halogen. So halogen here like chloride, fluoride, bromide, or iodide. So if we are talking about hydrogen chloride as a specific example, so the hydrogen will have a partial positive charge and the chloride will have a partial negative charge because the chloride will have more tendency to attract the electrons in the bond towards itself than the hydrogen. So it will have a partial negative charge and the hydrogen will have a partial positive charge. Now we have our alkene, which has a double bond. And now what's going to happen is that this hydrogen will be our electrophile. So to draw a mechanism for this kind of reaction, how it proceeds, we usually use these arrows, the one in red, these arrows. The way we draw the arrow is always the arrow will denote the movement of electrons. So we always start from the electron toward the electrophile. We never start by moving we never draw an arrow on the opposite way. So you never draw an arrow from the hydrogen which has a positive charge towards the double bond. You always have to start from the double bond or from the electron side into the other side. So now the hydrogen will add itself to the double bond as it will be attracted to this electron-rich source. So when the hydrogen is added, now this double bond will be broken and the hydrogen will be added here to one of the carbons. That will mean that the other carbon on the double bond will have a positive charge. And also as the hydrogen will leave without any electrons, this bond also will be broken and both electrons in this bond will go to the chloride. This is why we drew this arrow from the bond here towards the chloride. That means the chloride here will have a complete negative charge now. It's not a positive charge. The second step in this reaction will be the attack of the chloride will attack this positively charged carbon, which is called carbocation. Now the chloride with a negative charge, so we will draw the arrow from the chloride toward the carbon with a positive charge. So now a new carbon chloride bond will be created. So we will add the hydrogen halide or the HX to the double bond. One will have the hydrogen and the other one will have the halide. So you'll end up with alkyl halide. So we started with alkene and ended up with alkyl halide. Hydrohalogenation, there is the rate of the reaction will depend on the nature of the alkene and also on the nature of the hydrogen halide. So the more substituted double bond will be more reactive because it's going to be more electron rich. So if you have something like here, like ethylene, it doesn't have any substituents. It's all hydrogen. But this, if we have one propene, this carbon here has a methyl group. And the methyl group has tendency to give electrons towards this double bond. So this double bond here will be more electron rich, so it's going to be more reactive. If you have two other methyl groups, so if this carbon has two methyl groups like this one here, that means this double bond is even more rich or richer in electrons, so it will be more reactive. So the more the substituted double bond, or the higher the rate of the reaction, or the faster the reaction. For the alkyl halides, so the alkyl halides, the reactivity increases with the acid strength. So the more the acid strength of the alkyl halide, the faster is the reaction, or the more reactive is the alkyl halide. So we have hydrogen iodide is more acidic than hydrogen bromide, which is more than the hydrogen chloride, which is much more than hydrogen fluoride. So hydrogen iodide will have the highest rate of the reaction because it's much more reactive than the other ones. So what if we have different substituents around the double bond? So the two carbons that form the double bond are not equivalent. How will the hydrogen and chloride add themselves? Will it be that the hydrogen will be added to any of the carbons, or will it be more specific and add itself to one of these two carbons? There is a rule called Markovnikov rule, and Markovnikov rule says when there is an asymmetric substituted alkene react with hydrogen halide, then the hydrogen, which will add itself first, it will add itself to the carbon that had the greater number of hydrogen, which means I will make the carbon which is rich in hydrogen richer. So this is how I always like to say it. So I will make the rich carbon richer in hydrogen. So when I add the hydrogen, I will look at the carbon that has the higher number of hydrogen atoms, and I will add the hydrogen to that carbon, leaving the other carbon to form the carbocation, which means the halide then will add itself to the other carbon. Let's look at this specific example. So this is a cyclic alkene. So this is called cyclohexene, 1-methyl cyclohexene. It has here the double bond here has two carbons. The first carbon here, it's attached to one, two carbons. But the second carbon here, it has hydrogen and carbon. So this carbon has more substitutions. This carbon has a hydrogen, so it's richer in hydrogen, or it's more rich in hydrogen atom. It has more hydrogen atoms. So when we have the hydrogen chloride, then the hydrogen will add itself to one of these carbon. The hydrogen will not add itself to the first carbon where it has two other carbon atoms, but it will add itself to the carbon here at the second carbon, which already has a hydrogen atom because it has more hydrogen. So the hydrogen will add itself here. That will leave the positive charge on the other carbon. Now the chloride with the negative charge will attack the other carbon to give you the alkyl, then halide, the cyclohexyl chloride. So the substitution here, the carbon here, number 1, will have a methyl group and will have the chloride, and the other one will have the two hydrogens. This is the Markovnikov rule state this happens because actually this carbocation that is formed, when it's more substituted, when it has more substitution, then it becomes more stable. And when you form a more stable carbocation, it means that it's more easily formed, and then it will react faster. So it's very difficult to form this carbocation. It's much less stable, so it will not be formed. This is why this carbocation, because it's much less stable, it's not going to be formed, but this one is more stable and it will be formed. So the more the substituted the carbocation, the more it will be stable and the faster will be the reaction rate. Let's have another example, and now let's see if you can apply the Markovnikov rule. So again, now instead of adding hydrogen halide by hydrohydrogenation, now we will add water. Okay, so when we add water, we would need a catalyst, and the catalyst here is an acid, so any source of hydrogen atom. This is going to act as a catalyst. So the first step in the reaction is not the reaction of water directly with the double bond, but the addition of the catalyst, the hydrogen of the catalyst. It will fasten the reaction rate, and the reaction will proceed quicker. So the first step is that the hydrogen here from the catalyst will add itself to the double bond. According to the Markovnikov rule, it will add itself here because this carbon is less substituted. So this is the intermediate here, the carbocation that is formed after the addition of the hydrogen. Now this carbocation, we have the water and we have the oxygen has the lone pair of electron, and it will act as a source of electron or as a nucleophile. So it will add itself to the positive charged carbon or to the carbocation. So again, the arrow will come from the double bond from the lone pair of electron on the oxygen towards the positively charged carbon, and the water will be added as it is, and the oxygen now will have a positive charge because it donated all its electron on the lone pair of electrons to form the bond, so the oxygen will have a positive charge. So the next step then, that the oxygen need to get rid of one of these two hydrogens in order to be stabilized and will not bear a charge. So the hydrogen will now leave, but it will leave from the water. So when you have this with the oxygen has two hydrogens and a positive charge. So one of these bonds will break like this, and the electrons will go to the oxygen, and the hydrogen will leave um, uh, as a proton, hydrogen with a positive charge. So as if in the beginning when we added the hydrogen, we ended up with a hydrogen as well. So the catalyst here hasn't changed. We started with a hydrogen plus or a proton. We ended up with a proton as well that has left, and that will give us the cyclohexanol with a substitution as well on the carbon, the first carbon, the methyl substitution on the first carbon. The OH added itself on the carbon that is more substituted. This is to follow the Markovnikov rule, because the carbocation that was formed in this second step is the more stable one. The less stable one is not formed. So this one is not formed. The hydrogen will not add itself to this carbon which had a methyl group, because this is much less stable. So it will not be formed. Another example of the addition to double bond for alkene is the addition of bromine. So when you do your practicals this year, one of the experiments you are going to do is the dehydration of cyclohexanol. So when you do dehydration of cyclohexanol, you end up with a product which is cyclohexene. So cyclohexanol is the one that has an OH. So you remove water, dehydration meaning removing water. So you remove this OH and you remove hydrogen from the adjacent carbon, and then you end up with cyclohexene. A double bond is formed here. So to test this, the formation of the cyclohexene, we use what's called bromine water. So it's the bromine. So bromine water is colored, and when it adds itself to the bromine is added to this double bond to give you 1,2-disubstituted bromide, dibromide substituents at the end. Then the color of the bromine disappears, so it becomes colorless. This is how we test for the presence of the double bond. So how does this reaction happen? What is the mechanism of this reaction? Now we have the two bromide atoms, they are equivalent, and there is an induced dipole here. So one of the bromide in the bromine will have a partially a positive charge, and the other one will have a partial negative charge. So this is partial positive and this is partially negative. Again, the double bond of the cyclohexene will act as the electron donors, and it will attack the bromide with the partial positive charge to then form what is called bromonium ion. So this intermediate is formed now. It's like a cyclic structure, and the bromide will be form a bond with both carbons, not only with one. So the bromide now will give you this intermediate rather than with, this is different from the addition of hydrogen halide, where the hydrogen adds itself to only one carbon. Now the bromide will add itself to both carbons and it will have a positive charge. and then the other bromide will have a negative charge. Now the other bromide will attack one of these two carbons. According to Markovnikov rule as well, the second bromide will attack the carbon which is more substituted. So remember that the first bromide that is added to the double bond here is the electrophile. It's like the hydrogen, so it will add itself to the carbon that has less substitution or has more hydrogens. Now this is cyclohexene. There's no difference between the first and the second carbon, so it doesn't make any difference. But if you find that there is a methyl group, if let's say if this is a methyl group here, if this is a methyl, then this bromide will add itself to this one that has the methyl group that has more substitution. But this is not the case here, but you also need to know that. So the other bromide with a negative charge will add itself to one of these two carbons because they are exactly the same, and we will end up with the dibromo compound. For you at this stage, I wouldn't really care much about the stereochemistry of this compound, but for the students on the chemistry side, we will discuss that later when we discuss about the stereochemistry of cyclohexene. So don't worry much about the stereochemistry at this stage. So what if we said that we use bromine water. So if we have bromine and we have water in our medium, then the water will compete with the bromide in the second step. So the OH will compete with the bromide in the media, and then instead of having dibromo product, we were going to have a bromide on one side and a hydroxy group on the other side. So when you have bromine water, then an OH will be added in the second step to one of these carbons. So in aqueous media, there will be competition between the OH as a nucleophile and the bromide with the negative charge that has been formed. But if you have non-aqueous solution like carbon tetrachloride, for example, then it will be only the two dibromide will be formed. So to know what product you will get, you need to look at which solvent did you use. If it's an aqueous solvent, if it's water, then there will be competition between the Br and the OH. But if it's not, then it's going to be the dibromide. Another type of addition is the cis dihydroxylation of alkenes with permanganate. Again, in one of your practicals will be the limonene experiment. And in this experiment, you will use potassium permanganate to visualize the limonene on TLC. Limonene also is an alkene. And the reason why we visualize a limonene or alkene using potassium permanganate, because potassium permanganate will dihydroxylate the alkene, the double bond of alkene, and we will end up with manganese dioxide, which has a brown color. So now where the spot is, where the alkene is, will be colored brown because of the presence of manganese dioxide. So you can easily visualize it when you use the potassium permanganate. So this is the reaction of potassium permanganate with the alkene, and it will dihydroxylate, will give two hydroxyl group here, and eventually you will give you manganese dioxide, which is brown color, and this is the mechanism of visualization of the limonene or alkenes on the TLC using potassium permanganate.